So now we're going to look at a group of reactions known as redox reactions. And redox is basically an abbreviation for reduction and oxidation, right? So firstly, we need to talk about what do we mean by this term redox, what is happening in reduction reactions. And basically, what happens in these reactions is that you have the transfer of electrons from one reactant to another, right? So that is basically what a redox reaction is all about. Redox is basically what happens when you have the transfer of electrons from one substance to another. So, to look at this in more detail, let's define what we mean by the term oxidation and reduction. So, the substance that is undergoing electron loss is said to be oxidized, right? So, oxidation is what is happening when something is losing electrons. And reduction is the opposite, where the substance is basically gaining electrons. All right. And one thing you need to realize is that where you have oxidation, you must have reduction, right? If something is losing electrons, then another substance must be gaining electrons. So therefore, you simply cannot have one without the other. All right. So another term which I need to introduce to you is what is known as the oxidation state or oxidation number, which is basically a number that indicates the degree of oxidation of an atom in a substance. And we're going to talk more about how do we determine the oxidation number for a particular element or an atom, right? So these are represented by numbers, and there are rules for determining these numbers, which we will talk about shortly. Let me see here. So in a redox reaction, what happens is that one substance or one particular atom, more specifically, will undergo oxidation, as I said before, and that will be indicated by an increase in the oxidation number for that atom, right? And that corresponds to a loss of electrons. And then reduction is the opposite, where the oxidation number decreases for that particular atom, which corresponds to a gain of electrons. All right, so that's what happens in all redox reactions. All right, so there are some rules. I'm going to get out of this slide here and go to another slide, which I think gives the rules a bit more clearly. There are rules for determining the oxidation number of a particular atom in a molecule or ion. All right, so the oxidation number is, as I said before, a number representing the degree or level of oxidation in an atom. And another way of stating it is that it's the charge that the atom would have in a molecule or an ionic compound if the electrons were completely transferred. All right, so that's another way of looking at the oxidation number of an atom. So we're going to go through these rules. And let me just say that you don't need to memorize these rules per se, but you do need to understand them. And what you'll find is that with continuous use of these rules, you'll find that you basically get to know them, all right? So the first rule is that free elements, elements that are not combined with any other elements, have an oxidation number of 0. So any element by itself, not combined with anything else, automatically is assumed to have an oxidation number of 0. So here's a list of examples here, and in each case, the oxidation number of each of these elements would be 0. It doesn't matter if it's monatomic, diatomic, or polyatomic. The oxidation number of the element is 0 as long as it is not combined with anything else. Now, if you're dealing with a monatomic ion, then the oxidation number of that ion is equal to the charge on the ion. So, for example, in the case of the lithium plus ion, its oxidation number is +1. In the case of the iron 3 ion, the oxidation number is +3. In the case of the oxide ion, the oxidation number is -2, right? So any monatomic ion, the charge is the same thing as the oxidation number. Okay, now in the case of oxygen, and this is a rule specific for oxygen, the oxidation number of oxygen is usually -2, all right? Now there are certain exceptions. In the case of peroxides, such as hydrogen peroxide or anything that contains the peroxide ion, the oxidation number of oxygen in those compounds is -1, all right? So this rule is a bit more specific with respect to oxygen. In most compounds, the oxidation number of oxygen is -2, but in the case of anything that contains a peroxide ion, the oxidation number is -1 for oxygen, all right? Okay, the next rule is again one that is specific this time for hydrogen. The oxidation number of hydrogen is +1, but there are certain exceptions. And the exception is when you have the hydrogen atom bonded to a metal compound in a metal element in binary compounds, right? In these cases, the oxidation number of the oxidation number of hydrogen is -1, all right? So for example, the oxidation number of hydrogen in, let's say, hold on 1 minute. Why is this thing not writing? Okay, I need to go here first. Okay, so in the case of HCl, okay, what's going on? Oh, ah, just plugged this out accidentally. Okay, so in the case of, let's say, H2O, the oxidation number of hydrogen is +1. But in the case of, let's say, calcium hydride, the oxidation number of hydrogen here is -1, because in this case, the hydrogen is bonded to a metal, which in this case is calcium, all right? Okay, rule number 5. Group 1A metals, the oxidation number is +1, right, in compounds which contain them. For group 2A metals, the oxidation number is +2, and specifically for fluorine, its oxidation number is always -1 in compounds that contains fluorine. So I should add here a statement or something saying that in compounds containing these elements, in compounds containing these elements, whoops, these elements. All right. So for example, let's say sodium chloride. All right. The oxidation number of sodium in sodium chloride is +1, right? And sodium belongs to group 1A. Group 1A. It's a group 1A metal. Or let's say barium fluoride. The oxidation number of barium in this case is +2 because barium is in group 2A. And then fluorine, any compound that contains fluorine. For example, lithium fluoride, right? Well, the oxidation number of fluorine in this case is -1, all right? Okay, so that's rule number 5. These are group 1A metals, group 2A metals, and fluorine. Okay, and then now we get to a very interesting rule right here. It talks about the fact that the sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on that molecule or ion. So what this is saying is that if you have a molecule or ion and you add up all the oxidation numbers of all the atoms represented in that formula, then the sum of those oxidation numbers will be equal to 0 in the case of a molecule, or the charge in the case of a polyatomic ion. All right. So for example, let's look at this formula here. The question is asking, what are the oxidation numbers of all the atoms in the hydrogen carbonate ion? All right. Well, based on the rules that we talked about earlier, we know that hydrogen is always +1 in most cases, and oxygen is -2 in most cases, right? So there's no direct rule talking about carbon, right? But we can determine the oxidation number of carbon because we know that this is +1 for hydrogen, this is -2 for carbon, and we know that the net charge is -1. So basically the sum of all the oxidation numbers would be equal to -1 in the case of the hydrogen carbonate ion. So this is the setup right here. As we said before, oxygen has an oxidation number of -2, hydrogen has an oxidation number of +1. So therefore we can set up an equation where 3 times the oxidation number of -2, and there's a 3 here because there are 3 oxygen atoms, plus 1 for hydrogen, plus the unknown for the carbon. The sum of all those would be equal to -1, right? So therefore, the unknown for carbon, when we work it out, is equal to +4. So therefore, the oxidation number of carbon in this particular ion is +4. Okay, so that's basically how that is determined. And you can use this basically to determine the oxidation numbers of pretty much any other atom for which there are no direct rules concerning the oxidation numbers. Okay, so the next thing we're going to talk about now is how do we balance redox equation based on what we have covered. In fact, I'm going to stop this video here, and the next video, this will be the topic that we will be discussing. All right? Okay, until next time.